Okay, thank you so much for the invitation to come and give a talk to SAEMC. It's a great conference, so it's always good to be here. I just want to give a very quick thank you very much to Paul Heathersay. I note that he's leaving the department, and I wish to acknowledge his huge impact on the department, also on my career personally, so thanks very much, Paul. Okay, so Fleet Space is known as a geophysical contractor or geophysical services provider, particularly within ambient noise tomography, but there's a whole bunch of geologists that work there as well, would you believe? We're trying to deliver value to the clients by actually providing an interpretation of the geophysical method or geophysical data and to help people understand how to use this stuff. We had a fantastic project we've been working in the Macquarie Arc, and we've got a lot of work happening now in South America, particularly in Chile. We have people in the company who are who live there and work in Chile a lot, so it's fantastic to get out and about and see some of these other parts of Fleet's kind of global presence, if you like. Okay, the key points here. I'll just start with key points, right? Tomography. I need my glasses. I thought I could get away with it, but actually I'm getting old. Right, tomography, okay? ANT is just one example of tomography. It's 3D by nature, and because it's three-dimensional, it's not obscured by stuff at the Earth's surface, okay? So you can see in three-dimensional. And it's scalable. I'll give you an example and demonstration of that shortly. It's really good for imaging steep structures and structure in general, and that helps you to image and think about the architecture of your mineral system. It also picks up alteration really nicely because alteration results in change in velocity. Change in the mineralogy, often things like sericite and clays and so on will make a big difference to the mineralogy. The really key point to emphasise though is you've got to integrate multiple data sets for maximum effect. All you people understand that, but it's a really important point for Fleet to emphasise that we understand that as well. And that's why Fleet is working on multi-physics now. So at the moment, ANT is the stable kind of deliverable. Gravity is happening now as well. You'll see over the next year or so, a lot more other geophysical data sets will come out from Fleet that people can tap into. And that's all being shoehorned into an AI system, which is also a lot of work's going on in the back end at the moment, which they're calling Exosphere Discovery. And this will be all about reducing uncertainty or reducing geological uncertainty and providing drill targets through integrating multiple geophysical and, in fact, geological data sets. Okay, plug over. ANT. Now, I do not want to hear another person tell me that ANT is a new technique. It was made in the 1950s. People have been doing it for ages, okay? People have been doing it on batholiths. They've been doing it on fault zones. They do it at the continental scale like Carol showed you. So anybody who says it's a new technique is completely wrong. It's just passive seismic, okay? What do we image? We're imaging different rocks which have different velocities. The velocity really depends largely on the density, but also on the elastic properties, like how strong that rock is. And in passive seismic, what we're looking for is natural and anthropogenic sources. So basically like wind and waves produces subtle vibrations, but also you can feel it today. When the trucks go past, we can feel that on the ground. That's exactly what we're looking for. How does Fleet do it? Fleet has their own purpose-built geode. It's a seismometer, effectively, very small little device, just planted in the ground like you're planting your petunias. It's built here in Adelaide. There's a lot of smarts that are actually on the instrument itself. So you have this pre-processing, 1-bit normalisation and edge computing sitting on the geode. And why is that important? Because the geode itself is connected through the satellite. So you have to do these smarts on the geode, and then it's beamed up via Fleet's modem through to Fleet's satellites and partner satellites, which then can be sort of slurped down into the cloud, and people can be working on that data. So what that gives this is this near real-time, or near real-time data collection capability. That's important for two reasons. Firstly, it means you do your survey and you can do it quickly because we know when we've reached the signal to noise ratio that you need to get a good quality data set. Secondly, it means you can see the quality of data that's coming out as the thing's still in the ground, which is really important. It doesn't mean you have to wait for 6 months or 2 years or 5 years, however long, to collect the data. It's happening more or less in real time. It's a scalable, so basically most of Fleet's deployments are in the hundreds of geodes. You put out 100 geodes or so, and that's the sort of the way it's done. And you can do it at a small scale. If you want to do a small little area, you just pack them more densely, or if you want to see broader, you see it with a broader array. What are we measuring? These are designed to measure the surface waves, in particular the Rayleigh waves. So this is like the up and down motion of the ground by the seismic noise. So how does that tomography work? A geologist to explain the geophysics, okay? Different frequency waves travel at different depths. It's quite simple. If you have high frequency, they only see the small amount. If you have a longer frequency, they actually see deeper. So we're measuring across frequencies, and you will see deeper and deeper and deeper and deeper, depending on what sort of frequencies you're measuring. Now, what the geophysicists do is they take all that information of the different frequencies and they use cross-correlation. So we have a couple of geodes out the back here, a couple at the front, and a couple on this side. Now, my Nexus friends, please help me with this, but I'd like to demonstrate what a seismic wave looked like. If we start on this side, we're going to do the first ever SAEMC, first ever Mexican wave. Please, over here, there it goes. Bam, see that? Bam, 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 bam. And now, thank you everybody for... that looked really good from here. Imagine you had geodes everywhere, right? And as that wave comes across, your geode fires, then your geode fires later. It's as simple as time and distance. The cross-correlation is made between that signal at different geodes, and the geophysicists cross-correlate those different signals, and you're working out, you know, the distance that's happened there, the distance between there, the time it takes, and that gives you a velocity. If you do that with hundreds and hundreds of ray paths, or hundreds and hundreds of cross-correlations, you produce a three-dimensional image, and you do it at different velocities, so you get depth. It's pretty much as simple as that, although don't ask me to derive the equations, for goodness sake. Okay, I want to show you a few velocity models, just some examples of how it's being used, okay? I want to talk about scale reduction first, then something about lithology, and something a little bit about alteration as well. These are some use cases from the kind of work that Philippe's been doing, which has been fantastic to work with a whole bunch of different companies, such as Inflection Resources and Anglo Gold Ashanti, where we're working in the Macquarie Arc. This is looking at district scale. So this went really big, okay, as big as we could go, because Inflection had taken up a nice tenement package over 150 kilometre strike length, or contiguous tenements, so that the deployment could happen within that one area. They was basically put out 100 geodes, 150 kilometres long, as I said. It's about 1,800 kilometres squared. Took about 12 days to acquire the data, and then within 10 days you had a fully three-dimensional model of the seismic velocity down to about 5 kilometres. Now, Inflection and Anglo Gold were really keen to see this work written up, so we've actually published or submitted a paper on this as well. So if anybody wants to read that, just quickly grab that QR code. The preprint's up on that, but we'll get that in the Australian Journal of Sciences next year so you can see it. What does the data look like? Here's just a rotating image. This is one isosurface. So you take that 3D model and you just choose one particular isosurface and you map that, and it gives you a form. The orange colour is just the surface, and the blue colour is the depth, so that just helps the eye to tease out geometries, I guess. And what you'll see is that there are a whole lot of kind of intricate, almost mushroom-shaped. And right about now, when you're looking down the long axis, you can also see a cliff in the velocity response. So there's low velocity on one side, and then there's a cliff, and it's higher velocity on the other side. So that cliff corresponds precisely to the location of one of the major shear zones in the area. So now we're looking at that shear zone, we're imaging that shear zone very clearly in 3 dimensions. What's really interesting to me anyway is that some of the areas which have magmatic texture at this scale in the TMI are also showing these sort of mushroom, Pluton-like or laccolith sort of shapes, and some of them are actually connected through, seismically at least, into where that shear zone exists. I think this is a really interesting example of the potential that we're imaging this shear zone being a conduit for magmas that have come up and have sort of Pluton blobbed out, I guess extruded out, or sort of intruded into the surrounding volcaniclastics and volcanics of the Macquarie Arc. So a really interesting piece of work. Obviously that's really great. Now we've seen some structure. What are we interested in? Obviously you use your geochemistry and every other geophysical technique before you decide which one of those plutons is one of interest. And what you do then is you go in and you do a smaller scale survey. This is an example from the Reko Diq porphyry complex in Pakistan, world's biggest undeveloped porphyry with Barrick. So thanks to them for allowing us to show these images. But basically on the left-hand side you see a plan view of the 3D velocity model. It goes down to about 3 kilometre depth. And I've just highlighted one of the isosurfaces to bring out the texture in that again. And this isosurface corresponds very nicely to the location of porphyry bodies which are known because they stick out of the ground more or less, but also areas where there were porphyry intrusions slightly lower depth, which were then kind of could be followed up on. Okay, so now you know where your bodies are, obviously integrating your other geophysics as well at the same time. Then you go in and do a smaller scale survey over the area of interest, and this is at the kind of deposit scale, if you like. So this is 500 by 500 metre spacing down to about 1.8 or nearly 2 kilometre depth. Incredible textural resolution of these porphyry bodies here. The mineralisation and the alteration is both the high velocity features. They sit right on the edges of the porphyry bodies, often a high velocity, a lot of silica alteration there. And then where there's lots of the sericite, chlorite and carbonate alteration, you get low velocity features. And anywhere there's fracturing, which is typically what happens when these multiple porphyry intrusive bodies kind of intrude upwards. Mineralisation sits right on the edges of those velocity bodies. It's a really interesting example of deposit scale. So we've gone from the bigger scale and we zoom in on the areas of interest until you have nice little basically target zones to have a look at to do further work, such as drilling. But in principle, you can do that with any mineral system. This was just a porphyry example because a lot of work we've been doing is on porphyries. So the other obvious use case for tomography is looking at depth to crystalline basement, example from the Stewart Shelf. In this case, the red is slow and the blue is fast. But basically the blue part of where the Gawler is, the Gawler Craton basement there, shows up very nicely. It's not a one-to-one relationship with the drilling, but it's pretty damn close. 2700 velocity isosurface shows you where roughly you transition from sediments into the basement. But interestingly, even in the sedimentary rocks themselves, the quartzites versus the shales, they show up with a different velocity response. Well, not surprisingly, they're different rock types, they have a different velocity response. So this is a really great example. Now, if we just look in plan view now at Vulcan Prospect, where you have the gravity response on the left of those images, and the two other ones on the centre and the right are the ANT responses. The ANT in the middle one, where the mineralisation is, the ANT is sitting on or close to those gravity highs, which is really interesting. And then as you go a little bit deeper, the ANT low velocity zones seem to step away from that. It almost suggests like these are structural features, maybe they're related in some way to the architecture and the localisation of these hematite bodies. We're having a lot of success with unconformity related uranium in the Athabasca Basin. Again, the same principle here, the velocity contrast between the cover and the Proterozoic and Archean basement is massive. And so you can see that unconformity very nicely. That's really helpful for planning your drilling. But also within the cover sequence itself, within those sandstones of the Athabasca, you can get strong depletions in velocity where you have all your clay and texturally destructive alteration. That's exactly what IsoEnergy have shown. They did a survey over their deposit, smart thinking, and then they expanded it out and went, oh, look where else we have low velocity features, and they have been drilling into these things and are finding a lot of alteration exactly where the velocity is low. So it's a very, very good use case of it. So finally, closer to home, another use case of that has been our the Alfred project, which we've worked on with Thor. This one we also were able to publish a paper on this year if you want to have a look at some of that work. Again, alteration in this sense, supergene alteration or weathering, has completely destroyed the texture of a lot of this rock, and no wonder it responds as a low velocity features full of clays and things like that. But interestingly, the structural arrangement of these low velocity features extends into the basement itself, suggesting there's that connection between basement structure, the supergene, I guess, mineralisation, if you like, and the hypergene orientation of this mineralisation, and then the location of the supergene enrichment processes. So this was also a really nice example of that. Okay, final comments, ANT and beyond. Why, I want to emphasise again, why would you do real time? Because of course you can just leave the things out and come back in 6 months. We've got plenty of time. It's surprising that people, when they use this, typically one of the responses we get is that, yeah, that made a difference actually. It was really nice to see the data really soon after we laid out the instruments. It's really good. I don't know how many times I've taken a geochemical or other type of, geochronology is the worst, but other type of data set where you go and sample the rock. By the time you get the data back, you've forgotten why you've sampled the rock. This is really useful for making decisions, and especially in the exploration. And as I said, this ensures your data quality. We can see the data as it's coming out, and they do noise tests at the start of the deployment, and they say, okay, yeah, we need to shift the array or whatever. then that can be done in real time. So where to next? As I mentioned, multiple data types, imaging rocks using multiple petrophysical properties. Don't be scared of seismic velocity. It's just another petrophysical quality that rocks possess. We're all comfortable using density, and density is related to seismic velocity, so it's another way of looking at subsurface geology. Integration, both conceptually thinking about this, but obviously computational is a huge like something that needs to happen. A lot of joint inversions, and a lot of work on that is going on within Fleet as well. So I really look forward to seeing that. Hopefully, giving some updates on that sort of work, perhaps next year or in the future. So thanks very much for your time. Thank you.